Dear students, so welcome to the next video lecture for digital communication. So today we will be starting information theory. So this is a bit different from the general scheme of things that you have been going through so far in this module. So so far you have learned signals and systems, sorry, signal space concepts, and how to design an optimum receiver for binary and MRE channels, and then how to determine the probability of errors, and so on and so forth. So today we will start information theory, which mostly deals with the information that is contained in your digital communication signals, and how to quantify the information in your signals, and then how to find out how that quantity of information is getting degraded, okay, or the quantity of information is getting reduced because of noise. So far you were only looking into the communication system from only the receiver point of view, where whatever you were receiving in the presence of noise, you were trying to detect that, and design the receiver in a way that your probability of error is minimized. Today we will see things, I mean not today, but whatever we do from now on, we will see uh, the digital signals or the digital messages from the point of view of the information that they carry, and how that information gets reduced because of its propagation through the channel which has noise. Okay, so let's start. So information theory, basically this tells us how to define and measure information. So as I just said in the introduction, that information theory is all about quantifying the information that is contained in a signal. So that's what it says, how to define and measure information. So this part is important. It tells us how best to represent or code the information. Okay, so when we talk about code, there are different types of coding. So the first one is the source coding. So this is concerned with finding the most efficient way of representing the data. Okay, so right at the source, so if you remember that there are different blocks that you had for your communication system. So there was a source, and then there would be a channel, and then there would be a receiver. Okay, so right at the source you are doing source coding to find the most efficient way of representing the data that you are transmitting. Then you have channel coding. So next comes the channel. So you can also have channel coding or line coding, which is concerned with the best way of representing the data so that it will pass through a channel with the fewest errors. So remember that the channel will add noise, and channel coding deals with a mechanism so that the noise affects the signal in a minimum possible way, or in other words, the information will pass through a channel with the fewest errors. And then comes the encryption. So this is a coding which represents the message in a form, okay, so that it cannot be tapped by an unauthorized person. Okay, so the message is coded using a cipher, or a secret code to prevent unauthorized reception. And finally, you have error control coding. So this allows the receiver to detect and sometimes correct symbols that are received with error. Okay, so this part is the one that deals with the receiver. So you have come across error control coding to some extent in your wireless communication class, and also we have mentioned about error control in digital communication. But now, from now onwards, until the rest of this semester, we will deal with all these things. We will deal with information theory, we will deal with all this source coding, error control coding. Encryption we won't cover in this module because it's not a part of this module. You will probably learn encryption in information security module. And channel coding, we are also not going to cover much of channel coding, but definitely source coding and error control coding will be there in detail. So moving on, we are talking about information theory. So let's see what exactly is meant by information. So the concept of information is related to basically the predictability or scarcity of value. Okay, so what does that mean? The more predictable or probable the message is, okay, the more predictable or probable the message is, the less information is conveyed. Okay, so this is very interesting. So more predictable means what? So let's say more predictable. An example of a more predictable information would be, let's say the sun rises tomorrow. Okay, so this is if you look from the probabilistic point of view, the probability of this event, that the sun rises tomorrow, is almost certain. So this is one, the probability of this event. Okay, so this doesn't convey any information to you. If you think deeply, if I tell you that the sun will rise tomorrow, then you would say, what a big deal. I mean, everyone knows that. Tell me something more, tell me something new. That would be your reaction. So no information is actually conveyed by saying the sun rises tomorrow. However, let's say I say a less predictable thing. Okay, so let's say an example of a less predictable thing would be, let's say a vaccine for, let's say, coronavirus. Okay, will be out in 2020. Okay, so this has a low probability. Okay, I mean, of course, I'm not I don't want to be controversial, and I don't want to undermine the efforts of the scientists. So definitely they will come up with something. They probably have already come up with something, but let's say a vaccine that for coronavirus will be, let's say, out in the market. Okay, in the market in 2020. This is a very low probable event. This is not a event with probability 0, but the probability of it is relatively lower, or it is less probable. So if I say this, then this will be a breaking news, okay? So everyone will be very excited and, oh really, okay, so yes, this is a big news. So this particular statement conveys a lot of information, okay? So the point that I am trying to make is that there is a mapping between the probability of an event and the information that it wants to convey, and that mapping is inversely proportional. So we defined information I of an event xj by the logarithm to the base 2 of 1 over the probability of the event, okay? So this is the formal definition of information, okay? So you can see the more probable an event is, okay, the less information it conveys, and the less probable the event is, the more information it conveys. So moving on with this concept of information, so the units of this information are bits, okay? So this bit is different from the binary digit bit that you know. So this bit, this is a unit of information, and this comes directly from the fact that the information is defined in terms of the logarithm to the base 2, okay? So that's why the information unit is bit, okay? So if you define your information in terms of, let's say, logarithm to the base e or natural logarithm, then the unit of information will be nat, okay? Since the unit is since the base is 2, the unit is bit, okay? And this is different from the binary digit that we use elsewhere in digital communications and computer science. So this definition of information is consistent with the notion that as probability decreases, information increases. So we just talked about this in the previous slide with the two examples, okay? And since the probability of an event is always between 0 and 1, we must have the information of an event always greater than or equal to 0 with equality if and only if the probability is equal to 1, okay? And there is no such thing as negative information, okay? So, and all of this comes from this definition of information, which is defined in terms of the logarithm of 1 over probability. Now the use of the logarithm in the definition means that we can add the individual amounts of information we obtain when told the outcomes of a number of independent events, okay? So let's say, suppose we are told the individual outcomes xi of n independent experiments, and let the collection of outcomes be denoted by x, okay? So the probability of observing these n outcomes will be the multiplication of all these individual probabilities, because all of them are independent, okay? So the total information gained, okay, is given by this formula, by definition of information, and then this probability of x is the multiplication of the individual probabilities of x1, x2, x up to xn. So you can write this expression as the sum of the individual probabilities. So since there is a minus sign here, all of them are minus, and then these are actually the individual informations, okay? So this is I of x1, this is I of x2, and so on. So basically the total information is the sum of all the individual information of the different individual outcomes. Okay, so the logarithm definition is consistent with this intuitive fact that the total information should be the sum of the individual informations. Okay, so I will show you a video now which very nicely summarizes the concepts of information theory, and then we will come back after the video.
Imagine Alice has an idea and she wants to share it. There are so many ways to share an idea. She could draw a picture, make an engraving, write a song. Send a telegraph or an email. But how are these things different? And more importantly, why are they the same? This story is about the fundamental particle of all forms of communication. It begins with a special skill you likely take for granted: language. All language allows you to take a thought or mental object and break it down into a series of conceptual chunks. These chunks are externalized using a series of signals or symbols. Humans express themselves using a variation in sound and physical action, as do chirping birds and dancing bees, and man-made machines exchanging a dancing stream of electrical vibrations. Even our bodies are built according to instructions stored inside microscopic books known as DNA. All are different forms of one thing: information. In simplest terms, information is what allows one mind to influence another. It's based on the idea of communication as selection. Information, no matter the form, can be measured using a fundamental unit. In the same way, we can measure the mass of different objects using a standard measure such as kilograms or pounds. This allows us to precisely measure and compare the weight of, say, rocks, water, or wheat using a scale. Information, too, can be measured and compared using a measurement called entropy. Think of it as an information scale. We intuitively know that a single page from some unknown book has less information than the entire book. We can describe exactly how much using a unit called the bit, a measure of surprise. So no matter how Alice wants to communicate a specific message, hieroglyphics, music, computer code, each would contain the same number of bits, though in different densities. And a bit is linked to a very simple idea: the answer to a yes or no question. Think of it as the language of coins. So how is information actually measured? Does information have a speed limit? A maximum density? Information theory holds the exciting answer to these questions. It's an idea over 3,000 years in the making. But before we can understand this, we must step back and explore perhaps the most powerful invention in human history, the alphabet. And for this, we return to the cave.
Welcome back after the video. I hope you enjoyed the video and it gave you a nice overview and a nice understanding of the fundamentals of the information theory. So now going back to the original mathematical definition of the information. So note also that as the probability tends to 0, okay, the information gained by observing that event tends to infinity, because the information, as you saw, was this thing. So as this tends to 0, this term will be log of infinity. So the information will also tend to infinity. as the probability tends to 0. So this is again consistent with our starting discussion, where we were saying that, you know, lower the probability or less probable the event is, the more information it conveys. So let's take an example. So let's say an unbiased die, okay, is thrown, and we are told the result is a 4. How many bits of information have we received? Okay, so this is a very classic example which will demonstrate the information theory concepts and the probability concepts. So as long as an event can be defined with a certain probability, we can find out, or we can quantify the information conveyed by that. So when you are tossing a die, the result equal to 4 has a probability 1/6. Okay, so you have been through this before, you know, from your concepts of probability theory. So the information contained in the event that the result of throwing an unbiased die equals to 4, according to the definition of information, is log to the base 2 of 1/1/6, which is equal to log to the base 2 of 6, and the final result is 2.59 bits. As simple as that. So before moving on with the further concepts of information theory, let's look into some commonly confused entities. So a symbol, okay, which is a member of a source alphabet, this may or may not be binary. For example, a 2-symbol binary, a 4-symbol PSK, or a 128 symbol ASCII. Okay. Then the term baud, which is the rate of symbol transmission. So that means that 100 baud is equal to 100 symbol per second. Okay, so this is baud rate, and this is different from bit rate, because bit rate is the rate of information transmission in bits per second. Okay, so depending on whether a symbol, let's say, consists of 2 bits or 4 bits, etc., the bit rate will be different. So 100 symbol per second can turn up to 400 bits per second, let's say, if you are using QPSK. Okay, sorry, QPSK is 2 bits, so it will be 200 bits per second. Okay, if you use 16 QAM, let's say, then you are using basically 4 bits per symbol. In that case, you will have 100 symbol per second, or 100 symbol per second baud rate, translated as 400 bits per second. Okay, and finally, a message is a meaningful sequence of symbols. Okay, so now let us define another term called entropy. So entropy, denoted often by this symbol H, is defined as the average amount of information conveyed per symbol. Okay, so as you saw, your information itself is a random quantity. Okay, because it's basically a function of the probability. Okay, so if you find the expectation of this information, or the mean of this information, then what you get is basically your entropy. So entropy, H of x, is defined as the expectation of the information that you obtain. Okay, so suppose this random variable x has n possible outcomes. So you can define the entropy of x by this expectation of the individual information, and from the definition of expectation, you have um, this term, which is the weighted sum of the individual information, and the weight being the probabilities. So you have come across this before. You are familiar with this definition of expectation. We are exactly applying that here. So in terms of the probability, you can write I of xj as minus of log 2 pxj, and then you can define entropy in terms of this probability. Okay, so let's see an example. A binary source produces an outcome which is a 1 or a 0, and suppose the probability of 1 is alpha and probability of 0 is 1 minus alpha. So what is the entropy of the source as a function of alpha? So you can apply directly the definition of entropy and you will obtain this expression. Okay, so if you plot the entropy with alpha, okay, you will get a curve like this. So basically at alpha equal to half, that is when the two possible outcomes are equally likely, your entropy is maximum. So basically the maximum amount of average information, okay, so entropy is average amount of information, and the maximum amount of average information is conveyed when your symbols or the outcomes of the source are equally likely. Okay, so this is a very important result or concept in information theory. So moving on, since we talked about information entropy, so I want to show you another video on information entropy. So we'll stop here and I want to show you the video, and we will come back after the video.
Imagine two machines. They both output messages from an alphabet of A, B, C, or D. Machine 1 generates each symbol randomly. They all occur 25% of the time. While machine 2 generates symbols according to the following probabilities. Now, which machine is producing more information? Claude Shannon cleverly rephrased the question. If you had to predict the next symbol from each machine, what is the minimum number of yes or no questions you would expect to ask? Let's look at machine 1. The most efficient way is to pose a question which divides the possibilities in half. For example, our first question, we could ask if it is any two symbols, such as, is it A or B? Since there is a 50% chance of A or B and a 50% chance of C or D. After getting the answer, we can eliminate half of the possibilities and we will be left with two symbols, both equally likely. So we simply pick one, such as, is it A? And after this second question, we will have correctly identified the symbol. So we can say the uncertainty of machine 1 is 2 questions per symbol. Now, what about machine 2? As with machine 1, we could ask 2 questions to determine the next symbol. However, this time, the probability of each symbol is different, so we can ask our questions differently. Here, A has a 50% chance of occurring, and all other letters add to 50%. So we could start by asking, is it A? If it is A, we are done. Only one question in this case. Otherwise, we are left with 2 equal outcomes, D or B and C. So we could ask, is it D? If yes, we are done with 2 questions. Otherwise, we have to ask a third question to identify which of the last 2 symbols it is. On average, how many questions do you expect to ask to determine a symbol from machine 2? And this can be explained nicely with an analogy. Let's assume instead we want to build machine 1 and machine 2. And we can generate symbols by bouncing a disk off a peg into one of two equally likely directions. Based on which way it falls, we can generate a symbol. So with machine 1, we need to add a second level, or a second bounce, so that we have 2 bounces, which lead to 4 equally likely outcomes. And based on where the disk lands, we output A, B, C, or D. Now machine 2. In this case, the first bounce leads to either an A, which occurs 50% of the time, or else we lead to a second bounce, which then can either output a D, which occurs 25% of the time, or else it leads to a third bounce, which then leads to either B or C, 12.5% of the time. So now we just take a weighted average as follows. The expected number of bounces is the probability of symbol A times 1 bounce, plus the probability of B times 3 bounces, plus the probability of C times 3 bounces, plus the probability of D times 2 bounces, and this works out to 1.75 bounces. Now notice the connection between yes or no questions and fair bounces. The expected number of questions is equal to the expected number of bounces. So machine 1 requires 2 bounces to generate a symbol, while guessing an unknown symbol requires 2 questions. Machine 2 requires 1.75 bounces. We need to ask 1.75 questions on average. Meaning, if we need to guess 100 symbols from both machines, we can expect to ask 200 questions for machine 1 and 175 questions for machine 2. So this means that machine 2 is producing less information because there is less uncertainty or surprise about its output, and that's it. Claude Shannon calls this measure of average uncertainty entropy, and he uses the letter H to represent it. And the unit of entropy Shannon chooses is based on the uncertainty of a fair coin flip, and he calls this the bit, which is equivalent to a fair bounce. And we can arrive at the same result using our bounce analogy. Entropy, or H, is the summation for each symbol of the probability of that symbol times the number of bounces. Now, the difference is, how do we express number of bounces in a more general way? And as we've seen, number of bounces depends how far down the tree we are. And we can simplify this by saying that the number of bounces equals the logarithm base 2 of the number of outcomes at that level. And the number of outcomes at a level is also based on the probability, where the number of outcomes at a level equals 1 divided by the probability of that outcome. Number of bounces actually equals the logarithm base 2 of 1 over the probability of that symbol, which gives us our final equation. Entropy, or H, is the summation for each symbol of the probability of that symbol times the logarithm base 2 of 1 over the probability of that symbol. And Shannon writes this slightly different, which just inverts the expression inside the logarithm, which causes us to add a negative, though both formulas give the same result. So let's summarize. Entropy is maximum when all outcomes are equally likely. Anytime you move away from equally likely outcomes or introduce predictability, the entropy must go down. Now, the fundamental idea is that if the entropy of an information source drops, that means we can ask fewer questions to guess the outcome. And thanks to Shannon, the bit, which is the unit of entropy, is adopted as our quantitative measure of information, or measure of surprise.
So welcome back after that interesting video. I hope you enjoyed the video and it gave you a lot of insights into the fundamentals of entropy. So talking about entropy, there are certain bounds on the entropy, and that comes directly from the mathematical definition of entropy. So basically, if you consider a discrete source x with possible outcomes x1, x2 up to xn with their individual probabilities, then the entropy of the source is basically bounded between 0 to log of n to the base 2. Okay, and I leave this to you as an exercise. Okay, so to prove this, okay, that h of x is indeed between these two numbers. Okay, and we will discuss the solution later in some discussion session, but I want to see your solutions first. Okay, so this is an exercise for you. So now let's move on with joint and conditional entropies. So this is the scenario when you have two discrete information sources. Okay, and the first source x has m symbols, x1, x2 up to xm with the probabilities pxj, and the second source y has n symbols, y1, y2 up to yn with probabilities p of yk. So now suppose that each source outputs one symbol at the same time. Okay. So you saw the video on the information entropy where those two sources were emitting the symbols. So that similar concept is getting discussed here. So each source outputs one symbol at the same time, and in such a case we may regard this as a joint experiment with mn possible outcomes. Okay, denoted by this joint event xj comma yk, and the probability of any one outcome is the joint probability of xj comma yk. So now if the two sources are independent, then we can write that probability of xj comma yk is the multiplication of the individual probabilities. Okay, because this comma indicates the intersection. Okay, so this means xj and yk, and if both of them are independent, then you can write them as the multiplication of the individual probabilities, and if they are not, then you can write this joint probability using Bayes rule as the individual probability of xj multiplied with the conditional probability of yk given xj, or you can also write it in this form, probability of yk multiplied with the probability of xj given yk. Okay, so now if you want to find out the entropy or the average information gained when x and y each output one symbol, you call this as a joint entropy, and this is given by this this formula or this expression h of xy, where you have the double summation over all possible symbols x and y, and then the joint probability, and then the log of this joint probability to the base 2, and then the minus signs comes here. Okay, so now for independent sources you can write this expression and simplify this by applying the independence property. Okay, so the independence property tells you that the joint probability is the multiplication of the individual probabilities. So you can break the joint probability into individual multiplications, and then you can rewrite these terms where you can sum the first term over all k, and you can sum the next term over all j. So you can have these expressions, because if you sum all these probabilities of pyk over all k, okay, leaving the xj's separate, then sum over all this will give you 1. Similarly, this sum over all j will give you 1. So applying this, you simplify these two expressions as these two. Okay, so here you have probability of xj times log of probability of xj. Here you have probability of yk times log of probability of yk, and these are summed over j and k respectively. So you can write that these are actually the entropy of x and the entropy of y. Okay, so for independent sources, the joint entropy is actually the sum of the individual entropies. If x and y are not independent, then in that case you can apply Bayes' rule to write the joint probabilities in terms of the conditional probabilities. Okay, and then the first term you can sum over all k. So sum over all k of these marginal probabilities. Okay, so sum over all k of these yks given a particular xj is also 1, because this is summing over the marginal distribution, sum over the marginal distribution of y given xj. So if you take out the summation over k, then you will have this 1, and you will be left with sum of j equal to 1 to m probability of xj log of probability of xj. So that term will contribute to h of x. Okay, and then this term will contribute to h of y given x. Okay, so you will get, in case of non-independent sources, the joint entropy is equal to h of x plus h of y given x. So this is the definition of conditional entropy, which we have utilized in the previous slide for calculating this part. So the conditional entropy h of y given x represents the uncertainty remaining about y given that x is known. So since the sources are not independent, the observation of x tells us something about y, and therefore lowers our uncertainty about y. Okay, thus your conditional entropy h of y given x is always less than equal to h of y. Okay, with equality only for independent sources. So if x and y are independent, then the equality holds. Okay, so now moving on, let's define another term called mutual information. Okay, so the mutual information between x and y is denoted by I of x semicolon y, and this is defined as the information about y which is gained from observing x. Okay, so so you have h of y, and then this is the information that according to the definition of conditional entropy, this h of y given x, this represents the uncertainty remaining in about y given that x is known. Okay, so if you subtract this uncertainty that is remaining in y after you have observed x, will actually give you some gain in the information. Okay, so if you subtract this uncertainty, so this is basically the uncertainty remaining in y after observing x. Okay, so if you now subtract this uncertainty from the h of y, you are actually gaining in terms of the information. So when you are removing uncertainty, you are gaining information, right? So this is the definition of mutual information, which is the information about y which is gained from observing x. So you are observing x, and because of that you can define this conditional entropy of y given x, and this is by definition is the uncertainty remaining in y after observing x. So if you now remove that uncertainty from the original entropy of y, then you are actually gaining some information about y after observing x. Similarly, the mutual information between x and y can also be written as the information gained in x after observing y. Okay, so you can also write h of x minus h of x given y. Okay, so the information about y which is gained from observing x is the same as the information about x which is gained from observing y. So I of x semicolon y is equal to I of y semicolon x, and you can try the proof yourself. Okay, so these are some of the properties of mutual information. Okay, so I of x semicolon y is always greater than equal to 0 with equality if and only if x and y are independent. Okay, so if x and y are independent, then you don't gain anything about x, let's say, by observing y, or you don't gain anything about y by observing x. So therefore your mutual information is equal to 0 when your x and y are independent. Also the mutual information is less than equal to the minimum of hx or hy. Okay, and finally the mutual information is equal to hx plus hy minus h of xy. So I would ask you to try and prove all these properties. Okay, try yourself and try to prove all this property from whatever you have learned so far, and then if you have any doubts or if you are facing any problems, then we can discuss it in the live sessions. So let's do an example to understand the concept of mutual information. So let's say an unbiased die is thrown and the random variable x reports if the result is odd or even, and the random variable y reports if the result is low, which means 1, 2 or 3, or high, which means 4, 5 or 6. So now you are asked, what is the mutual information between x and y? So let's say the probability of getting an odd or an even is half. Okay, so if you are considering the random variable x which reports whether the result is odd or even, the entropy of that is defined or calculated from the definition of the entropy as half of log to the base 2 of 2 and then half of log to the base 2 of 2. So that is 1 bit. Similarly, for low and high also the probabilities are half, because you can get these three numbers half of the times and these three number half of the times on the average. Okay, so h of y is also from definition 1 bit. Okay, so we may find the joint entropy using the joint probability. So the joint probability of being odd and low is 2 over 6. So you can verify these yourselves. The joint probability of odd and high is 1 over 6. The joint probability of even and low is 1 over 6, and the joint probability of even and high is 2 over 6. So this leads to h of xy from the definition as 1.92 bits. Okay. So now you can find mutual information also by using the individual entropies and this relationship. So h of x plus h of y minus h of x y. So this will give you 0.08 bits. And the conditional entropy h of y given x by using this relationship, so that will give you 0.92 bits. So now moving on, let's check into another concept called redundancy. So redundancy is basically the difference between the actual entropy of a source and the maximum entropy, H max. So the source could have, if its symbols were independent and equiprobable. Okay. So as you saw in one of the slides before, that if you are plotting the probability of the source, like the entropy is maximum when the source probability are equiprobable. Okay, you saw that you were plotting hx with alpha, right, where alpha and 1 minus alpha are the probabilities of the source, and you saw that when alpha equals to half, you get this maximum. Okay, so H max, so this is H max, let's say. Okay, so the maximum entropy that you can obtain minus the actual entropy that you get, let's say, because let's say your source symbols are not equiprobable, so that difference H max minus H is called R, or the redundancy. So for an M symbol alphabet, the source, if they are equiprobable, then the probability will be 1 over m for all the symbols of the source. So the maximum, so H max will be by definition log of 2 over m. Okay, so this log of 2 over m, log of m to the base 2, minus h, this is your redundancy. So let's do an example. So find the entropy, redundancy and information rate of a 4 symbol source A, B, C, D with baud rate of 1024 symbols per second and symbol selection probabilities of 0.5, 0.2, 0.2 and 0.1. So basically your source is emitting 4 symbols, A with probability 0.5, B with probability 0.2, C with probability 0.2 and D with probability 0.1. Okay, so and also the source is memoryless. Okay, so now let's see what will be the entropy, redundancy and the information rate of a 4 symbol source with the baud rate of 1024 symbol per second. So the entropy you can easily calculate from the definition. So all these probabilities are given to you and you can just apply the values in this formula to get the entropy as 1.761 bit per symbol. and this is a 4 symbol source. So the maximum entropy you can get if the symbols are all equiprobable. So equiprobable means 1 over 4 is the probability, and for that the H max will be log to the base 2 of 4 minus the actual entropy that you calculated, so that is 1.761. So the maximum entropy could have been 2, the achieved entropy is 1.761, so therefore the redundancy is 0.239 bits per symbol. So the information rate is basically the baud rate times the entropy. So 1024 symbols per second multiplied with 1.761 bit per symbol will give you 1.8 kilobits per second. Okay, so this is your information rate. So now let's move on, and now that we have defined information, we have quantified information, and we have defined entropy, and we have also defined the mutual information, okay, and also the conditional entropies. So all these terms are being defined. Now we can actually apply this knowledge of information theory that we learned so far to find out information loss due to noise. So you have so far, before this lecture, you were just looking into the receiver and trying to find out the error that was introduced because of noise. Now we will look into the concept of noise from the information theoretic perspective. So what is the quantifiable information loss due to noise? That we will try to see. So the information transmitted by a memoryless source is related only to the source symbol probabilities. Okay, so that is defined as this. So let's say I is the information of the transmitted symbols, and the information capital I of the source is given by this, okay, from the definition of information. Memoryless source is basically a source in which the symbols selected are statistically independent. Okay, so now let's say in a noiseless channel, the transmitted symbol will always be as the received symbol. So whatever you are transmitting, you are receiving the same thing. Okay, so the information gained at the receiver is identical to the information transmitted. So if you defined Rx, that is the information gained in the receiver, that should be always equal to the information transmitted, and that is equal to this. Okay, but for a noisy channel, however, there is some uncertainty about which symbol was actually selected at the source. Okay, so the uncertainty is related to the conditional probabilities. Okay, that the symbol I was transmitted given symbol J is received. Okay, so you can define effective entropy, okay, by this term. So for a noisy channel, basically from intuition you can say that the information received should be less than that transmitted by an amount related to the uncertainty or equivocation in the receiver's knowledge of transmitted source symbol. So whatever is the entropy, you are deducting a term called equivocation, and then you are defining the effective entropy, and the equivocation is basically defined by this, and this is basically related to the negative information that is contributed by noise. Okay, and this is defined by all those conditional probabilities that are associated to the channel. Okay, so you saw this concept when you were studying the discrete memoryless channel, where you are transmitting something, and because of the error introduced by the channel because of noise, you are receiving something else, and you are defining the channel with some conditional probabilities or transition probabilities. So the same concept is actually borrowed here. So let's say, given that you have received J, what is the probability that you transmitted I? Okay, and those probabilities actually define the contribution due to the noise. Okay, and if you use those probabilities in the definition of informations, those probabilities will give you basically the negative information that you are losing because of the noise. Okay, and that negative information is called equivocation, and if you deduct that information from the entropy H of the source, then you are getting the effective entropy that the receiver is getting. Okay, so you can write E in terms of these two terms, E dash and E double dash. Okay, so where E dash is actually these type of terms. Okay, basically E dash is the term where actually you are making an error. Okay, you are receiving a J, but you are transmitting an I. Okay, so these type of terms are separated, and that contributes to E dash, whereas E double dash are those terms where you are receiving I and you are transmitting I as well, so there are no error. So the no error terms are given by E double dash, and the error terms are given by E dash. Okay, so you can write E as E dash plus E double dash. Okay, you can also write E as this. Okay, so let us see an example to get this cleared. Okay, I mean, don't get confused much by these expressions. Okay, if you apply these conditional probabilities, okay, then things will be much clearer. Okay, so let's take an example and use the actual values of these conditional probabilities into this definition of equivocation, and then try to find out how you can get this effective entropy. Okay, so let's say a three symbol source A, B and C is there with the following transition matrix. Okay, so when you are transmitting A, you are receiving A with probability 0.6, you are receiving B with probability 0.2, you are receiving C with probability 0.2. Similarly, when you are transmitting B, you are receiving B with probability 0.5 and you are receiving A with probability 0.5. There is no transition from B to C. Okay. Similarly, when you are transmitting C, you are receiving C with the highest probability, and then there is also a certain chance of receiving B when you are transmitting C, and then receiving an A is 0. Okay, so so with this and also this information that the specific transmission probabilities of A, B and C given by 0.5, 0.2 and 0.3, you are asked to find the symbol reception probabilities Pi Rx, the equivocation, the source entropy, and the effective entropy. So you can look into this example and try to match your knowledge about discrete memoryless channels. Okay, so you can say that you have three symbols A, B, and C. Okay, and let's say, so this is the transmitter side, and in the receiver side also you have A, B, and C, and then you can map this transition matrix like this, as you did in case of your discrete memoryless channels. So A to A transition is 0.6 probability, A to B 0.2, okay, and A to C is also 0.2, okay. Now B to A is 0.5 and B to B is 0.5, B to C is 0, okay, and C to A is 0, but C to B is 0.333 and C to C is 0.667. So this is also a kind of a discrete memoryless channel, and you are asked to calculate all these received symbol probabilities, okay, and then the equivocation, the source entropy, and the effective entropy. So what we will do, we will calculate the symbol reception probabilities by using the conditional probabilities. So probability of getting an A in the receiver is probability of transmitting an A, and then the conditional probability of receiving A given an A was transmitted. Okay, so these values are given. These conditional probabilities are your transition probabilities that you can pick up from this matrix. Okay, so and then all these source probabilities, okay, are given. So these are basically your a priori probabilities. So you get 0.4. Similarly, you can calculate probability of receiving a B and receiving a C as 0.3 and 0.3 respective. To find the equivocation, we require the probabilities this, okay. So probability that you transmitted I given you receive J, which can be found in turn from these probabilities and the received probabilities using Bayes rule. Okay, so basically if you apply Bayes rule, okay, so you can write that probability of A transmitted given A is received is the joint probability divided by this you have already calculated here, and this you can write, the numerator you can write in terms of the conditional probability that A is received given A transmitted multiplied by A transmitted. So this part is given in the transition probability matrix. Okay, so you can pick those values from here and then calculate all these values. Okay, so for all these, okay, you can calculate the values by applying Bayes rule and all the transition probabilities. Okay, so you can calculate all these values. Okay, and if you are done with calculating all these values, then you can just apply the expression of equivocation like this. Okay, from definition of equivocation, and in that definition you can see you have two terms. One is that given A received, what was the probability of A transmitted. So these are the no error terms. Okay, or in other words, these are the E double dash terms. So these are the E double dash terms, and these are the error terms, so these are the E dash terms. Okay, and you keep on writing these terms for A received, okay, then for B received, and then for C received, and then you can sum up all these values and you will get the equivocation as 1.08 bit per symbol. And the source entropy is again calculated from definition. So the source symbols has these probabilities 0.5, 0.2 and 0.3. So you can calculate from the definition of entropy. The source entropy has 1.48 bit per symbol, and then finally you can calculate the effective entropy as H minus E. So 1.48 minus 1.08, so 0.4 bit per symbol. Okay, so we will stop here and we will continue in the next video lecture. Thank you.